Physics 2, Lab 2. So the purpose of this lab is similar to the first lab where we're determining the charge on a piece of charged tape. However, we're using a different model. Here we're modeling the charged tape as a one-dimensional charge rod with the charge evenly distributed on the surface, as opposed to the point charge model. And we're going to determine this using a computational model to simulate it. So the models and fundamental principles are the same as Lab 1, where we have the Coulomb's law for electric force, Newton's second law of momentum, and the force of gravity. But we also have the formula for the superposition of an electric field of a charge rod on a horizontal symmetrical axis, that is the x-axis that divides the charge rod into two. And we also have the electric force in terms of the electric field that we will use in our coding. So a preview of the results is that the charge of the tape using our new model is approximately 2.4 times 10 to the power of negative 8 coulombs, which is much more accurate, as we will see, compared to the point charge approximation that we used in the last lab. The assumptions in this lab is obviously air resistance is ignored. The charge is uniformly distributed across the surface of the tape. The charge is treated as a one-dimensional charge rod with negligible thickness. Both tapes have the same amount of charge, and the mass of each tape is approximately 1 gram per meter. So the experimental method used in this lab is the same, where we charge two tapes by ripping it off another piece of tape, thereby transferring an excess charge on each one. We lay one of the tapes across two neutral objects and hover another one below it, such that the top one gets repelled and hovers over it. Then we can use Newton's second law as well as the Coulomb's law to calculate the amount of charge on the object. So using the formula for the superposition that we discussed in the introduction, we get, and when we plug in our values listed here, we get the value for the charge to be around 2 times 10 to the power of negative 8 coulombs. So the way that we're going to approximate the charge using the distribution model is by using a computational model. So first we're going to define all our constants as well as the mass of the tape and our estimate of the charge of the tape that we will adjust later. We also define functions such as the net electric field, as well as the way that we're going to model our line charge as a series of individual point charges across a line. We then write a for loop to calculate the contributions of each of these individual point charges on the upper point charge, thereby creating a superposition of electric fields. Finally, this is the code that will help display the results. Coding this will give us the following results. So if we use the value of Q that we calculated in Lab 1, which is using a point charge model, then we can see in the results that the magnitude of the electric force is far smaller than the magnitude of the gravitational force. So this is not consistent with our observations. On the other hand, if we approximate Q by trial and error, so we adjust Q until the magnitude of the electric force and the magnitude of gravitational force are balanced, we find that it is about 2 times 10 to the power of negative 2.4 times 10 to the power of negative 8 coulombs. And this is a lot closer to the actual value that we calculated, which was about 2 times 10 to the power of negative 8 coulombs, thus showing that the distribution model is far more accurate than the point charge model. So let's discuss these results. So what if I had modeled each of my tapes as a single point charge like in the previous lab? So in the point charge model, we got the charge of one tape to be about 1.2 times 10 to the power of negative 8 coulombs, while in the distribution line charge model, we get it to be about 2.4 times 10 to the power of negative 8 coulombs, while the true value that we calculated is about 2 times 10 to the power of negative 8 coulombs. This shows that the point charge model is off by about 8 nanocoulombs, while the line charge model is off about 4 nanocoulombs, thus cutting our error by about half and therefore is far more accurate. So why do these estimates differ? This is because the line charge model is closer and because it accounts for the contributions of the charges of all the points on the tape. Since the top tape is not sufficiently far away from these bottom, these contributions are very important and we cannot estimate it as just a single point charge. Nonetheless, there still exist sources of error in this experiment that lead to a 4 nanocoulomb difference from the true value. These include the fact that the charges may not have been evenly distributed on the surface, which is an assumption we made. The thickness of the tape was definitely not considered. There were difficulties in measuring the distance between the tapes, and the charge on each tape may have not been the same. Nonetheless, we still get a more accurate result using this line charge model.